Welcome to Chemistry at Honeyga High School. I'm Brian Brown, and today we'll be looking at our last set of notes from Chapter 7, where we'll be getting into metallic bonding. Now, metallic bonding in some ways is kind of a hybrid of what was happening with molecular and ionic bonding. In some ways, it's kind of like sharing. In some ways, it's kind of like ion attractions. Now, metallic bonding is a force of attraction between free-floating valence electrons and positively charged metal ions. Now, this is often referred to as the electron C, and you can see why in the animation here. What basically happens is we have a bunch of metal atoms. Metal atoms are not noble gases, so they're not stable. Now, normally they would react with a nonmetal. The nonmetal would steal their electrons. In other words, they would give it up. You would form cations and ions, and the two would attract. But when you're with a bunch of other metals, you have a whole bunch of other ions which are all looking to do this, or atoms, which are all looking to do the same thing, lose their valence electrons. So what happens in metallic bonding? Because we know we can have pure metals. So we know that there has to be some sort of bonding that exists to make them at least somewhat stable. So the model is the electron C model. And what happens is if all of the atoms of the metals give up their valence electrons and they're shared and free to move around, then you end up with metal cations attracted to free moving valence electrons. And that ends up with a very fluid type of bonding that we know as metallic bonding. So in the fact that you have cations being formed, that's kind of like ionic. And in the fact that you have sharing of these valence electrons throughout the structure, and these are delocalized, free-flowing moving electrons, makes it in some ways a little bit like a covalent bond. So you basically have a bunch of cations that won't be attracted to each other, but they will all be attracted to the nearby free-flowing valence electrons. And as long as multiple cations are holding on to or attracted to the same electrons around them, then in essence they end up held on to each other. So that is the type of bonding that happens inside metallic substances. And that's why alloys would be a blending of metals fundamentally doing the same thing. And those metal ions, or I should say metal atoms, which are becoming cations, are all giving up their valence electrons around them. So on a particle level, what this would look like as a visualization is what you see here. Now the yellow tennis balls are the metal cations, and the hazy white cloud represents the electron cloud of delocalized electrons moving throughout the structure. So when I play the animation, what you see is a bunch of these metal cations with free-flowing valence electrons between them, and those free-flowing valence electrons are in constant motion. And because the cations are each holding on to these electrons in between them in that valence electron cloud, they're ended up bonded to each other. So that would be a animation of what metallic bonding looks like on a particle level. Now there's a short movie called Metallic Bonding I'd like you to watch that does a nice recap of some of these ideas and shows some nice animations of some of the different things we're going to talk about. So it's a short movie, so make sure you take a look at that after you take a look at the notes. Now, because that's the type of bonding that exists within metals, that's going to affect the properties of the metals themselves. Now, this type of bonding is actually a fairly strong type of bonding. So most of the time, metallic substances are metals at room temperature. In fact, mercury is the only metal in the whole periodic table that this would not be true for. So they're typically solids because this is typically a stronger type of attraction. Sometimes they have very high melting points, just like ionic compounds do. Sometimes, like in the case of mercury, you end up with lower melting points. But as a general statement, metallic bonding typically leads to a stronger type of bonding. So typically we have higher melting points in the metals, but it does vary depending on the actual strength of that bonding. Now, because of the fluid nature of that valence electron clouds, they're great conductors of heat and electricity. And they're also very malleable as you pound on them, like you can see with the hammer here, because of the fluid nature of the type of bonding. You can push these cations all over along with their free-flowing valence electrons, and yet they still retain their solid form. So when you hit it with a hammer, it dents and it flattens out. It doesn't shatter. So it's not brittle like an ionic compound is. It's very ductile, which means you can pull it into a wire and it will still maintain its solid form. It also tends to be very shiny due to the fluid nature of the moving electrons that are within it. So the very nature of the bonding itself heavily influences the properties of the metal. Now, one thing that can happen with metallic bonding is we can actually mix different types of substances together. Now, one of them has to be a metal, but sometimes they're a blend of all metals. And the atoms that exist within fit into this matrix of free-flowing valence electrons. So a mixture of two or more elements, one of which being a metal, would be an example of what an alloy is. Now, fundamentally, there's two types of alloys I want you to understand. And it really depends upon how we're substituting and what we're substituting. In a substitutional alloy, alloys of the metal are replaced by atoms of similar size. So what's really happening is in this free-flowing nature of the substances. If we have a substance that's relatively close in size, when we put it inside the structure, it just fits in there with the others. So you're substituting an old position metal with the new substance. So literally it's taking its place. Good examples of this would be sterling silver, which is really common in jewelry, brass, and 10 karat gold. 10 karat gold has gold with things like copper blended in it that are base metals that change its properties and make it a little bit more durable in terms of it's not as malleable and as soft. It's a little bit harder, but yet it's also significantly cheaper because it's not all made out of gold. And there are a number of different types of alloys that are substitutional alloys. So if the atoms that are replacing the metal are of somewhat similar size, it's a substitutional alloy. Now, in an interstitial alloy, you have very small atoms that actually fit between the metal alloys or the metal atoms that are inside there. And a good example of this would be carbon steel. So we have basically iron atoms with small amounts of carbon that have been substituted in between. So they're not taking the place of the iron atoms, they're sitting in between them and bonding to the iron atoms, and they end up changing the properties of it. So carbon steel is a much stronger, less malleable type of steel, but yet it's also more brittle because of the carbon that we're putting in there. So it's stronger, but yet it's more brittle. So that would be an example of an interstitial alloy. So take the place of the substitute, that's substitutional, and fitting in between the spaces, that would be interstitial. Now, just to do a quick review of the different types of bonding here. This is something I saw online. I thought it was cute. And it does a nice review of the ideas we're talking about. So it's bonding through the viewpoint of dogs. So in this particular case, the bones would be represented by the valence electron. The chlorines took it from the other one and ended up with Cl minus, and that left the other one a Cl plus, opposite charge attract. That would be, of course, ionic bonding. So what would this one be? You got a bunch of dogs, each giving up their valence electron, and those valence electrons are free to move throughout. That would be metallic bonding. So that's just a quick review of a couple of different types of bonding that we looked at. And that ends our notes over Chapter 7.